Flip classroom video for maths, WJC Maths Unit 3, Pure Mathematics, M2.3.7 D2, which is applying integration by substitution. The previous video was introducing the idea of integration by substitution. This is about applying it to problems. So it's becoming more common for them, for the examiners, not to tell you what substitution to use, which after all, if you met a problem which required integration in real life, you're unlikely to have the instruction use such and such. You've got to choose that substitution. But remember, the idea of the substitution is to make the integration look easier. So I've given you one here, the integral between 1 and 0 of x cubed bracket x squared plus 1 all to the power 4. Now clearly we could expand that. X squared plus 1 all to the power 4 would give me 5 terms. And then I could multiply through by an x cubed, and I can integrate each of those 5 terms separately. But that's a lot of tedious work. I'd want to be able to do it much faster, and I'd like to be able to do it more efficiently. So you've got to decide which of those aspects it's worth choosing to make your substitution. And I would generally go with the thing that is being raised to a power. So in this particular case, I'm going with x squared plus 1. That's my substitution. So if I let u equal x squared plus 1, the implication is that du by dx equals 2x, and hence x equals 1/2 du by dx. So I can get rid of an x from my x cubed at the front. I can simplify my bracket to simply become u to the power 4. So it's starting to look better, but I've still got an x squared there. What I don't really want to do is to consider, because it's an x cubed, to consider 1/2 du by dx all cubed, because I only want a du by dx there for my implicit bit. As I said, there was an alternative that I mentioned in the previous one, which you may see used. It's up to you. I'm changing my limits because that's what I tend to do. It's not necessary. So if u equals x squared plus 1, if x equals 1, then 1 squared plus 1 is 2. And if x equals 0, nothing squared plus 1 is equal to 1. So my integration becomes the integral between 2 and 1 of x squared u to the 4 multiplied by 1/2 du by dx, because that was what x was. Notice I've split up the x cubed with respect to x. Now I've got to get rid of that x squared plus 1. Oh, sorry, the x squared, my apologies. And I'm going to use my x squared plus 1, because if u equals x squared plus 1, then it's fairly obvious that x squared is equal to u minus 1. So I've got that bit there, no real problem. So now I can change my integration all the way through. It's all in terms of u's. 1/2, I've taken the half out because it's a constant, simply because it makes my integration easy to deal with. My limits are 2 and 1, and I've got u minus 1 times u to the 4 with respect to u, or du by dx, because of my implicit again with respect to x. So obviously I'm going to expand out that bracket u minus 1 times u to the 4. So I'll get u to the 5 minus u to the 4 du by dx, and really I'll bracket it, or I could distribute the du by dx if I wanted to. Wouldn't tend to, because it tends to clutter up the writing. So u to the 5 minus u to the 4 du by dx. With respect to x, my limits are still 2 and 1. I've got a half out in the front there. So fairly obviously the integral of u to the 5 is u to the 6 over 6, and the integral of u to the 4 is u to the 5 over 5. My limits are 2 and 1. It's a really easy piece of work to come on now. So I said, remember what I said, that integration by substitution is to make the work easier. So plugging my values, 2 to the 6 is 32, well, it's actually 64, but it's 64 over 6, hence I've got 32 over 3. 2 to the 5 is 32, so I've got 32 over 3 minus 32 over 5, minus, putting in 1/6 minus 1/5. So I'm going to end up with 1/2 of 43 over 10. I tend to write top-heavy fractions. There's no point in writing 4 3/10 when I can write 43 over 10. Fairly obvious. And a half times that is 43 over 20, no real problem. Sometimes they'll give you a substitution. Sometimes the substitution looks a bit strange. So this one, it's suggesting I should use the substitution u is equal to 4 plus 5 tan x to evaluate this horrible thing. And you can see it's a vile looking integration, but it's quite doable. Changing my limits, if x equals pi by 4, u is going to be equal to 4 plus 5 times the tan of pi by 4, and the tan of pi by 4 is 1, so therefore it's 4 plus 5, which is 9. And if x equals 0, then u is 4 plus 5 times the tan of 0, which is 0, so therefore I get u equals 4. Now it's interesting, you should spot there that these are square numbers. Therefore, that fits in with that square root that's above the 4 plus 5 tan x. So, use my substitution. If u equals 4 plus 5 tan x, then du by dx, the differential of u with respect to x. Clearly, the differential of 4 is nothing because it has no gradient function. Differential of 5 tan is 5 sec squared x. That's on your formula booklet should you wish, but it is a good one to remember. And therefore sec squared x equals 1/5 du by dx. Now the reason I've written that is that I had spotted, and the reason I've spotted this is I've been doing this for a very long time, that the cos squared on the bottom, remember that cos squared, a reciprocal of cos squared, in other words 1 over cos squared, is actually equal to sec squared. So therefore I could rewrite my integral between pi by 4 and 0 of root of 4 plus 5 tan x over cos squared x as the root of 4 plus 5 tan x sec squared x dx. So I'm going to end up with the 1/5 from the du by dx, the root of u, because that was my substitution I've got to do, du by dx, and my sec squared, or the cos squared, has cancelled in that particular movement there. So I'm going to end up with quite a nice easy integration to do. Okay, I've got the implicit bit in there, but if you accept the sleight of hand that cancels the dx's, all I'm doing is integrating u to the half. Root of x is u to the half, so I get that one. And raising my power by 1, a half plus 1 is 1/2, or 3 over 2, dividing by that new power. 1 divided by 3 over 2 is 2/3. Between my limits 9 and 4. So 1/5, 2/3, 9 to the power 3 over 2 minus 2/3, 4 to the power 3 over 2. And it's worth square rooting first of all. We only would consider in these particular cases positive square roots. Square root of 9 is 3, 3 cubed is 27. So I've got 2/3 of 27, well clearly 3 goes into 27 9 times, so that first term becomes 18. And then square root of 4 is 2, 2 cubed is 8. So I'm going to get 18 minus 16 over 3. Okay, 1/5, I'm not quite sure why that bracket, first bracket is more strident than the other, but hey. Right, now 18 is 54 over 3, and 54 over 3 minus 16 over 3 is 38 over 3. 1/5 of 38 over 3 is 38 over 15. Leave it in that form. You can, there's nothing wrong with writing it as 2 8/15, but what purpose? 38 over 15 is a perfectly valid answer. Now there's a couple of common integrals for you to watch out for. They are on your formula booklet, but they don't look quite the way you're going to get them. From the formula booklet, the integral of 1 over a squared plus x squared is given by 1 over a tan to the minus 1 of x over a. And I have no doubt at all that your teacher in subsequent lessons with you. So therefore what this is saying is what I've just said there. The integral of that is equal to this thing here, where a is a constant. And you should watch out for this one, because especially when you come to deal with partial fractions, and you'll get more of these in a subsequent video. The other one to look out for is this one, the integral of 1 over root a squared minus x squared is arc sine, which, remember, that doesn't mean the reciprocal of sine, because that's something different. Cosec means arc sine, the angle whose sine is x over a, and the restriction on that is that ax, or the mod of x, must be less than a. Clearly the reason for that is if x was bigger than a, when I square it and subtract it from a squared, then I'm going to get a negative value, and we really don't want to be playing around with the square roots of negative functions, because they give rise to an area of mathematics that we have yet to study.